Well, we've looked at the electric field and charge distributions from charged conductors and charged shells. So it's time to kick it up a notch here. And now we're going to consider what happens when we put an insulating shell around a charged conductor. So we have Q, regular charged conductor, radius cap R. We're going to put an insulating shell, which has radius 2r. And this insulating shell has a uniform volume charge density. I'm sure you're glad for that. So it's a non-conductor. The charges are locked in place, and the charge density is uniform. So this is going to make it a little more interesting. One condition of the problem is figure out the charge density of this insulating shell so that the total charge is 0. So the net charge being 0 for the whole thing requires this insulating shell be negative Q. Now, the volume charge density is charge over volume. So the charge is negative Q. The volume is the volume of the entire thing minus the volume of this inner conductor. So minus Q over V of the 2R volume or sphere minus the 1R sphere. So that's minus Q over 4/3 pi 2R cubed minus 1R cubed. Well, 2R cubed is 8R cubed. So this whole thing is minus Q over 4/3 pi 7R cubed. And the volume charge density is then minus 3Q over 28 pi R cubed. Now, that was a good first step. Let's now figure out the electric field for R less than big R. Well, that's easy, 0. Now between R and 2R, that's where it gets interesting. We won't finish it on this slide. Let's get a start. So we'll put a Gaussian surface somewhere in there, radius R. The flux, we still have spherical symmetry. That's nice. So the electric field is radial and it's uniform on that Gaussian surface. So closed integral of E dot dA is EA, Q enclosed over epsilon 0. Well, now let's very carefully and methodically consider the electric field, which simply is Q enclosed over epsilon 0A. But what's Q enclosed? Q enclosed by the Gaussian surface through the insulating material. That charge enclosed is certainly enclosing all of the center Q, but now it's also enclosing rho V shell. The volume charge density, charge per volume times volume, is charge. This charge, represented by rho V shell, is the amount of charge contained in the insulating spherical shell that's enclosed by the Gaussian surface. Hope that makes sense. Divided by epsilon 0A. A is 4 pi r squared. So the key then is, first of all, this is key to understand this, and then let's just expand that. Well, what's the volume of the shell? The volume of the shell will be the volume of the entire Gaussian surface sphere, which is this, 4/3 pi r cubed, minus 4/3 pi r cubed, namely the radius of the inner conducting sphere. So take off that volume, and you have the volume of material, of insulating charged material, uniformly charged, to give the entire amount of charge that's enclosed by the Gaussian surface, over epsilon 0, 4 pi r squared. Now, so we have to multiply this by rho. We already got rho. And plug that value in. That's not so cool because here is the volume, the value for the volume charge density. Well, when we do this, the algebra, I believe, comes out as follows. And indeed, that wolf expresses the sentiment we all share, which is that it'd be nice to forget about this algebra and just go back to living off the land in Alaska. But nevertheless, if we can just get our eyes to come back to this for a moment, it's not really too bad, because as we'll see, this thing has to be consistent with the charge going to 0 at 2r. So let me just suspend that and let's finish the problem, and I'll come back to that thought. So when the radius is greater than 2r, we know, because of the way we picked this, that we're now enclosing at 2r 0 total charge, because the charge of the insulating shell is minus q. So E then is 0, because no charge is enclosed. So let's graph the E field. Between 0 and r, of course it's 0, and then it spikes, as is typical. And it reduces in such a way to come to 0 at 2r. This should be horizontal right here. And then in all of space beyond 2r, the electric field is 0 as well. No charge enclosed. So back to this formula. When r is too big R, that's when it goes to 0. So if this is 2r, we have 8r cubed minus r cubed is 7r cubed. 7r cubed over 7r cubed is 1. 1 minus 1 is 0. And indeed, that's consistent with our plot here. Okay, this time we're going to consider a uniformly charged long cylinder. And we're going to figure out the electric field in all space. So it's got radius cap r. Volume charge density is constant. And here's a Gaussian surface inside this thing. It looks like a solid cylinder, but it's not. It's just a Gaussian surface within. And it's got radius little r, so, and length L. The flux through that Gaussian surface, closed integral of E dot dA, which is Q enclosed over epsilon 0. The charge enclosed by this Gaussian surface is going to be related to the volume charge density times the volume. So EA, I can write this integral as EA because the E field is uniform and radial on the Gaussian surface. And Q enclosed is rho times V, volume charge density times volume. And that volume is pi r squared times the length. The area of the end times the length is the volume. So we can write the electric field. This divided by epsilon 0a, the area of this Gaussian surface. Be very careful to distinguish between those. Rho pi r squared L over epsilon 0, 2 pi r L. The surface area is, if you go all the way around this, the length is 2 pi r times L. We can unravel this cylinder, and that would be the area of the wall, the sheet area. So it's very important not to confuse area and volume. It's easy to mess those up when you're working problems. Make sure you always distinguish. Am I looking for volume or am I looking for surface area? We just did both. Nice cancellation, giving us rho r over 2 epsilon 0. Now let's look at the electric field outside. So let's put a Gaussian surface, wrap it around the entire cylinder. It's a nice looking Gaussian surface, if I say so myself. And there is little r and length L. So now, once again, we have cylindrical symmetry, namely that the electric field is uniform and radial on the Gaussian surface. So that's Q enclosed over epsilon 0. Well, what is the charge enclosed? The charge enclosed is all of the charge on this cylinder underneath the Gaussian surface. So that could be expressed in terms of a linear charge density. There's a certain amount of charge per length of the original cylinder. So E is equal to charge enclosed lambda L over epsilon 0 A. Now be careful. Area 2 pi r circumference times the length. That's the area of the Gaussian surface. No, keep note in all this analysis, we're not worried about the ends for the surface area because there's no electric field going to the ends. So we didn't include that here. So there's the electric field, lambda over 2 pi r epsilon 0. Notice the striking difference between these two expressions. Namely, inside we have the electric field proportional to r. Outside, the electric field is inversely proportional to r. That's quite explicable when you consider the fact that inside, the charge enclosed by this volume is proportional to the volume, which is R cubed for a cylinder. And then it's getting less when you go for a cylinder of charge or a line of charge. The charge diminishes by 1 over R. So 1 over R is fighting this R squared increase in total amount of charge, giving us 1R proportional to 1R. Whereas down here, we're not enclosing any more charge outside of the cylinder, and it's just inverse R away from a uniform line of charge. So there it is, inverse R. Okay, now just interesting to recognize that the two expressions for the inner and outer electric field have to come together when little r is equal to big R, because that's the transition point. So for r less than r, we have the electric field rho r over 2 epsilon 0. For r greater than big R, we have that proportional to the linear charge density over 2 pi epsilon 0 r. So when r is equal to r, let's see how they come together. So lambda equals charge per length, and that's equal to rho v over L, and v is equal to pi r squared L at radius r. Okay, so that's the entire volume of the cylinder over that length. These L's go away. So now E is equal to lambda over 2 pi r epsilon 0. That's this. And so I'm substituting big R for little r. And now putting in lambda, which is rho pi r squared, divided by 2 pi r epsilon 0. And we see that we have the electric field being rho r over 2 epsilon 0, which is what we have as an expression for r less than r. So they do come together at little r equal to big R. Now let's graph it. So there is the electric field from 0 to r. We start at 0 and we end, since it's proportional to r, it's a straight line. Value is given either by this or by this. Same thing as we just saw. Then, beyond big R, we have inverse R. And so at 2R, it's the value. And at 3R, we have this value. So that expresses the electric field in all of space for this problem.